Good day everyone, this is Team Assignment 2 utilizing ICAS software presented by Team 7. The case study assigned for our group was regarding azeotrope formation, where the problem consists of finding all the binary mixtures that form an azeotrope with ethanol at 1 atm, where the other compound is an acyclic compound having boiling temperature ranging from 300 Kelvin to 400 Kelvin. Now, let us take a look at the ICAS software using ProCam. First, we type in the title at problem title. Next, we click on generate acyclic compound. As for the pre-selection, we refer back to the question for structural constraint where acyclic compound, including hydrocarbon, aldehydes, acids, ethers, and esters are considered using as the basis set of the group. After clicking the pre-selection, they will be appeared as the selected groups at the bottom. Next, for the extended problem control, further structural constraints will be considered where the maximum number of group as well as the functional group will be set to 8 and the maximum number of same functional group is set to 2. And lastly, we need to remember to click on the perform database after search as well as generate isomer. Next, for further property constraints that needs to be considered, we click on the non-temperature depth props, and from here we right click on the screen for it to show the different options they have, and in this context we actually need to set the normal boiling point with the minimum of 300 Kelvin and maximum of 400 Kelvin. As for how we unselect gold, we just normal click on the normal boiling point option and untick gold.
So after that, in the mixtures property, we have to perform mixtures calculations. So the bonding we pick is original VLE, and the calculation type is VLE calculations. And for the conditions, we are actually maintaining at room temperatures and atmosphere pressures. And so in the questions, we are trying to find binary mixtures that form azeotrope with ethanol only. So in this interface, we have to search ethanol out. So how we search it is by clicking the edit button, and then we search for the string for the ethanol, and then we click add and OK. So after that, there will be three ethanol will appear in the interface. For the second column, we have to insert its mole fractions. In this case, it will be 1. So based on the property constraint, beside the specific boiling point constraint, the liquid miscibility with ethanol also need to be checked. So after the mixture's property calculations, we are also need to perform azeotrope and miscibility calculations. So in the azeotrope part, we are trying to form azeotrope between ethanol and the binary mixtures that we generate. So for the miscibility part, we are trying to find mixtures that is totally miscible with ethanol. So in the mole fraction step will be 0 to 1 in 10 step, and the temperature range is 300 Kelvin to 400 Kelvin in 5 step. So once we generate the result will come out something like this.
Alright, so here we show the result from ProCam. Our goal was to find binary mixture that form azeotropes with ethanol at 1 atmosphere pressure. Focusing on acyclic compounds with boiling point between 300 Kelvin and 400 Kelvin. ProCam helped us to check the structure and property constraint, like whether the compound is fully miscible with ethanol. The result will give us several compounds that fit this criteria. So it giving us a good option for further analysis. Here is one of the solutions ProCam came up with, a binary azeotrope that fully miscible with ethanol. From the azeotrope property here, you can see that this candidate forms a low boiling homogeneous azeotrope with ethanol at 348.55 Kelvin and 0.62 mole fraction. It meets all the structural and property constraints we set, including the boiling point range and miscibility. So we use ProPrep to dive deeper into its property to confirming it is a solid candidate. This solution will show us that the ProCam is a useful tool for tackling problems like this.
In the ICAS software interface shown on the left, we define the problem as a binary isotrope with ethanol in bracket totally miscible. Various compound classes were pre-selected to guide the software in generating potential candidates. For this case, we selected ethers, esters, aldehydes, amine, and acids. The software uses an integrated data bank scan to match the generated compounds with stored physical and thermodynamic properties, as shown in the pop-up on the right. 1,2-dimethoxyethane was identified as a matching candidate for this azeotropic system. The results generated by ICAS provide critical data about the system, such as the boiling point. The normal boiling point of the identified compound is 377.82 Kelvin, confirming its compatibility with ethanol under typical process condition. And as for the miscibility, the table at the bottom right shows that the mixture remains totally miscible and across all mole fractions 0 to 1 and temperatures ranging from 300 Kelvin to 400 Kelvin. So these outputs are valuable for understanding the behavior of the ethanol 1,2-dimethoxyethane system, especially when designing processes that involve isotropic mixtures such as solvent recovery or isotropic distillation. So ICAS requires specific inputs such as the molecular structure of the compound, relevant compound identifiers like the CAS number, property categories to analyze. For this case, the compound 1,2-dimethoxyethane was either retrieved from the software's database or input manually. So the PropRep module uses group contribution methods and connectivity indices to estimate the compound's properties, such as Marrero and Gani, Constantino and Gani, Jobeck and Reid. On the left, the software provides key physical and thermodynamic properties such as melting point, boiling point, critical temperature, critical pressure, and also molar value. And on the right, the PropRep module visualizes the molecular structure of 1,2-dimethoxyethane, and this helps confirm the compound's connectivity and verify the presence of functional groups like ethers which directly influence the estimated properties. And the software also calculates connectivity indices such as zeroth order CI 4.23, first order CI 1.89. So these indices serve as a quantitative descriptors of molecular structure contributing to the accuracy of the property estimation.
After putting all the constraints and the limitations that we derive from the problem statement, we already find the another candidate compound, which is methyl isopropyl ketone. As we can see the skeletal structure of the methyl isopropyl ketone and also the description, which based on the order description. As we can see, the first order description is two groups of methyl, one group of CH, and one group of CH3CO. And as you can see at the second order description, the group name of the methyl isopropyl ketone is methyl isopropyl ketone itself, or CH3COCH. And from the first group and the second order description, we can already find the boiling point of the property, which is the 364.41 for the first order and 367.55 Kelvin for the second order, which is really reliable because it falls under the limitations or the range given in the problem statement, which is between 300 to 400 Kelvin. Now, lastly, this is the property sheet of the candidate that we chose, which is methyl isopropyl ketone. As we can see, the another synonym of the methyl isopropyl ketone is 2-butanoin 3-methyl. And this is the CAS number and the formula of the methyl isopropyl ketone, which is C5H10O, and the SMILES configuration itself. And the Antoine equations, which is the parameters of A, B, and C, are given in this property sheet. As we can see, the Antoine A is 6.74163, Antoine B is 1131.929, and Antoine C is 199.235. These parameters can be used to evaluate the vapor pressure at certain temperature of the methyl isopropyl ketone. And that's all from me. Thank you.